Hello, my name is Unal Goktas, and today I will be talking about our latest developments on symbolic solving of partial differential equations. So thanks for joining us today. And this is the abstract. Probably you have seen this already. So first, I will start with classical PDE problems, heat, wave, and Laplace problems. And then also I will talk about our new development on fairly modern approaches like uniform transform method due to Focus and his co-workers. And then I will conclude with the concluding remarks. So let me start with heat equation initial value, boundary value problems. I will start with rectangular coordinates from 1 dimension through 3 dimension. And the first example that I want to show is the insulated bar problem. Here, both ends of the bar are insulated, and the length of the bar is assumed to be 30. So we have Dirichlet, we have Neumann conditions on both ends. And since the bar is insulated, the derivatives are 0. So the solution is returned in terms of an infinite sum. In the background, we are using separation of variables and eigenvalue, eigenfunction expansion. So for practical reasons, we set infinity to be 500. And if you plot the solution, then the plot looks like this over here. So this was the insulated bar problem. The next problem is when we have a heat source in the system. So this is the heat source, internal heat source in the system. This time we have Dirichlet boundary conditions, and the solution is again in terms of an infinite sum. And if you plot the solution, then we get a plot looking like this one here. In the solution, the first 2 terms are due to the inhomogeneous boundary conditions at x equals 0 and x equals 30. The next problem is when we have a heat loss in the system. So this is the term representing the heat loss. Again, we have Dirichlet boundary conditions, and the solution is an infinite sum as expected. And when we plot the solution setting infinity to 500 for practical purposes, we get this as the plot. For the same problem, if we neglect the heat loss and return back to the original problem, so we remove the heat loss and plot that as well. So the first plot here is the problem with the heat loss, and the one next right to it is the plot of the problem with no heat loss. Okay, this time we have a semi-infinite rod. So suppose we have a very long rod, so we can treat it as semi-infinite. And in this case, we just have one boundary condition at the starting x value. So the solution is returned in terms of error function. And if you plot this one, the solution will look like this. So in this first one, we had a Dirichlet condition. And if we change the condition to be a Neumann condition, then again we get a piecewise error function solution. And this time the solution will be looking like this one here. Next, suppose we are at the center of the very long rod. So in this case, we can assume that it extends from minus infinity to plus infinity. So this time we have an infinite rod, and therefore we don't have any boundary conditions. We just have initial condition. The solution is returned in terms of error function again. And when we plot the solution will be looking like this here. Suppose for the same problem, we have a source generating heat, and the source function is sines function. And this time the solution will have extra pieces due to this source. And when we plot the solution will look like this time. So another method that we use is transforming hard equations into simpler ones. And for instance, suppose we have a diffusion equation with this term here. So we want to get rid of this b times u partial x. And for this, we use this transformation. And this leads us to this simpler heat equation. And for this example, we will be showing the trick of this transformation. So this equation is, this problem is solved by using this transformation. And once the solution is found, the plot looks like this. So now we have two-dimensional heat equation. In the input, the first piece is the two-dimensional heat equation in rectangular coordinates. The second one is the initial condition, and the rest are the boundary conditions. And for this example, we have a mixture of boundary conditions like Neumann, Rubin, and Dirichlet conditions. So the solution is, again, an infinite sum, but this time we have a double summation. And here, the solution is valid provided that this condition is satisfied. So this condition is for the eigenvalues. So in this summation, we need to compute the eigenvalues satisfying this condition first, and then compute the summation. So for practical reasons, first let's compute the first 100 eigenvalues satisfying this condition, and then we can compute the summation. So this is the truncated solution. We truncate at the 100th eigenvalue, and the solution will be looking like this. And so we can see how it changed through time. Okay, this time we have a three-dimensional heat equation. Okay, the first piece is the three-dimensional heat equation in rectangular coordinates. And again, we have a mixture of boundary conditions. We have Neumann condition, Rubin condition, and Dirichlet condition. Again, the solution is valid provided that the eigenvalues satisfy this condition. So again, we need to first compute the eigenvalues satisfying this condition, and then we can compute the truncated solution for practical purposes. So suppose we compute the first 202 eigenvalues this time, and then suppose we, in this summation, we let the other infinities to be 50, like here. So if we compute the truncated solution, and if we plot the counterplot 3D for t equals 5, the plot will look like this. And for the same solution for t equals 15, the plot will look like this. So this covers the rectangular coordinates for the heat problem, and now we work with polar and cylindrical coordinates. The first problem is a thin circular plate with circular symmetry. Since we have circular symmetry, we have no theta dependence. So the first piece here is the heat equation in polar coordinates with no theta dependency. And we assume that at r equals 0, solution is bounded. So we just have one boundary condition for r equals 1. So if we compute the solution and then plot it for setting infinity to 100, and the solution will look like this over here. And if we plot the same solution over a circular domain for t equals 0.45, then the solution, the plot will look like this. The next problem is, this time we have no circular symmetry, so we have theta dependency. So in this case, we have r, theta, and t as independent variables. And solution is valid provided that this condition is satisfied. So similar to the rectangular case, we first need to compute the eigenvalues satisfying this condition. So for practical purposes here, we computed the first 50 eigenvalues, and then we sum up to 50, and this gives us the truncated solution. And if you compute this manipulation, then we get a manipulate function. Okay, the next problem is we have a cylinder with angular periodicity. So this time the boundary conditions are periodic. So here we have a boundary condition relating negative pi to pi, and so this. In this case, we look for solutions with periodic boundary conditions, and we compute the solution. And again, we have a double summation, and we compute the truncated solution. And if we plot for t equals 5, then the plot will be looking like this. And for t equals 15, plot will also look similar, very slight difference. Okay, this covers the heat problems, and now we are ready to start with wave problems. Similar to heat, we will be starting with rectangular coordinates. And the first one is the one-dimensional wave equation, but this time we have a general type wave equation with restoring terms. This is the restoring term, and this is the damping term. So the solution, as expected, is an infinite sum. And if you plot the solution will look like this. The next example is when we have inhomogeneous boundary conditions. So we have inhomogeneous boundary conditions over here. And so these terms come from the inhomogeneous boundary conditions. And if we compute the truncated solution for infinity going to 1000, and if you plot the solution, the plot will be looking like this. Next example is when we have wave equation in unbounded regions. So now we are working over the half line, and the problem is this. So we have initial condition like this, and boundary conditions are Neumann type. Sorry, one of the boundary conditions are Dirichlet condition, and the other one is Neumann condition. So the solution is a piecewise solution given in this form. And if you plot the solution, then we get a plot looking like this. So suppose we have a vibration problem and there are forces acting on the system, and the conditions are the boundary conditions are given as Neumann condition. So since we have okay, the solution is found as this one, and if you set infinity to 100 and then plot it, the plot will be looking like this over here. Next, we have two-dimensional wave equation. So the first piece over here is the two-dimensional wave equation in rectangular coordinates, and then we have the initial condition, and the rest are the boundary conditions again. And again, we have a mixture of boundary conditions. And the solution involves a double summation. And if you plot the truncated solution and animate it, the solution will be varying over time like this. Okay, here we have a three-dimensional wave equation. We have a triple summation in the solution, and for t equal 5, if you plot the counterplot 3D, the solution will be looking like this. And for t equals 15, a slight variation in the plot. Next, we have a symmetric vibration of a circular membrane. So we switch to polar and cylindrical coordinates. And in this case, since we have symmetry, there is no theta dependency. We just have r and t in the system as independent variables. And the solution is found as infinite sum. And when we plot it, the solution will be looking like this here. The next example is the vibrating drum head. So the solution again is an infinite sum, and we computed the truncated solution and run an animation, and the solution will be varying over time. Okay. Okay. Next piece is examples on Laplace problems. Again, starting with rectangular coordinates, we have a potential problem in a rectangle, and the solution is an infinite sum, and the plot will be looking like this here. So the next example is potential along an infinite strip or infinite thin plate. So if we want to study steady state temperature distribution in a thin plate, this is usually a type of problem that we deal with. And the solution involves an integral. So for practical purposes, we switch from integrate to n-integrate for numerical evaluation. And if you plot the solution will be looking like this. Next, Laplace problem in 3D. So in this case, like similar to the heat and wave problems, we get a solution with double summation. And when we plot a counterplot of this solution, the solution will look like this. And now we have a Laplace equation in a thin plate in polar coordinates. So here the solution is found in terms of polylog, and when we plot the solution will be looking like this here. Next example, we have a potential in a thin plate with periodic boundary conditions. So we have periodicity here. These are periodic boundary conditions, and the solution turns out to be fairly simple. And we can easily plot the solution, and the solution will be looking like this. The next example is we have a Neumann problem in an annulus, and we have a piecewise solution, and the solution is valid inside the annulus. And when we plot the solution will be looking like this here. Okay, this covers our latest developments in classical problems. And the next one I want to talk about is what we have done with unified transform method. So this is a method, and it has been widely studied, initially developed by Focus and his co-workers. And it has three cases. The first case is the whole line case. And in this case, we do not have any restriction on the order of the derivative. So for instance, in this example, we have gone up to order 12. So it could be any order, provided that it satisfies the conditions of the method. And the solution is returned fairly simple, and we can easily check that it's true. The next case is half-line case. Suppose we have Schrödinger equation with zero potential, and we have this initial condition and this boundary condition. Since we are working on half-line, we just have one boundary condition. And the solution involves unevaluated integrals, and these integrals are usually very hard to compute, even numerically. And they have also suggested a method for computing these integrals numerically. So the last case is the finite interval case. So this time, again, we have Schrödinger equation with zero potential, and we have Dirichlet and Rubin conditions. So the method determines how many boundary conditions are required, and you need to provide so many boundary conditions in order to make this method work. And again, we have a fairly long solution with integrals. So this covers the finite interval case. So we have developed a vast variety of new and improved methods for solving PDEs symbolically. And we have been testing our developments on collection of problems. And for instance, for the collection from Articulo's book, I mean, we have quite high success rates, like 93%. And for the next release, we are working on a manuscript which is describing all these developments and also other aspects of PDE solving, symbolic PDE solving in DSolve. Let me quickly show a few pages of it. So it starts with introduction, and so it talks about method of characteristics, and it has, okay, so this is still a very raw draft, and we are working on it. So hopefully in the next release, it will be complete and will be available to the users. So this is all I have for today. And if you have any questions, I will be happy to answer. And if I missed some of your questions over the chat, I will make sure I get back to you after the talk.